Thank you. So I'm really happy to be here, first of all. So I've been here since the first edition of hardwear.io, and it's always a pleasure to be here. So I wanted to say this as an introduction. And then we'll jump to the topic of this talk, which is integrated circuit security. So here at hardwear.io, we are speaking a lot about hardware security, but there's a field which is I don't know how to call it, but it's really focusing on the silicon circuits and how you can abuse them, because at the end of the day, you are all running software on a piece of silicon, and if this piece of silicon is not secure, I don't know if your software can be considered as secure. So I will start with the motivation and say that, all right, that's an integrated circuit. And as you can see, it's everywhere in our day-to-day life. So if somebody can hack inside one of these devices, he can do a lot of things like stealing your identity or copying your product, or, I don't know, remote controlling your car or killing you if you have a pacemaker. So just because of this, I think this kind of security must be considered as something which is really important. And when it comes to the attacks, so there's three kinds of attacks, from non-invasive, where you just play with signal, inject fault with glitches and things like this. Semi-invasive attack, where you start to play with lasers, UV light, this kind of stuff. And the invasive attack is to me, it's not known enough. All right. It's old. I mean, the first invasive attack were done 25 years ago or so. But my point here will be that, when I started to work in that field, I was working in the payTv field, and I was basically dumping firmware from smart cards, So there was piracy, heavy piracy. And we wanted to know what the pirate could have learned from the official device, to build countermeasure that would be targeted for them to lose at the end. So that was a pretty cool game, but I soon realized that the level of security told by the certification scheme and what I could feel doing invasive attack had no link, So a high-ranked card was not more secure than a low-ranked card sometimes. It was even the opposite in some cases. And for this reason, I decided that I should do something, So basically, I was building a company which is called Texplain, and we want to give to anybody a piece of the cake, give to evaluation lab better tools to evaluate the security, taking into account the silicon itself. And we do consultancy for integrators to be able to choose the right chips for their targets. And we help vendors also to make better products and so on. So that's just a start. But my main point here was I should change common criteria. That was my goal in 2013. I was starting the company saying in 6 months, maybe I will have changed the rules, which is I don't know, I was young, So in fact, it took me much more time. And as a result, you will see that I was failing really badly. But anyway, I'm still here to talk about this. So basically, I was at hardwear.io 2015, giving a talk about one of those secure smart cards that is in the field, and it's a payTv smart card. And what I was showing is I could dump the card, with some effort, but I could dump the card in a time that I was considering as super nice, 2 weeks. So you make pictures of the chip, so I don't count this in my 2 weeks. But then once I have those pictures, 2 weeks after I can dump the card. And that was the idea. And I was that's supposed to be pretty great, So I did an attack, which was known. And this is the amount of reverse engineering I had to do on the target device, so not so much, I would say. And yeah, I could do an attack which is called linear code extraction. This attack exists since 25 years, right? It's nothing new here. So, okay, I did the talk and everything went well. And at some point, I decided to try to rank the attack. Okay, so let's say I'm an evaluator now. So I took the common criteria thing and started to put some points here and there. And I arrived at a result which is, I don't remember, close to 31 points. All right. 31 points. If you score something higher, that's secure. All right. The attack you just build is called a residual threat, and nobody cares. Basically, it doesn't exist. So I was close to this mark, and I was like, oh yeah, so maybe I have something to tell people and say, look, we need to change the rules. So I tried, and my result is like, I failed. Once again, you know, because somebody said, no, that's not how the things are ranked. Okay. So now it's like, it comes to, how can I understand the rules, you know? So basically what I want to do during this talk is talk about the situation like in the 2000s, you know, when I started basically, and then see how the attack was ranked. And I'm trying now to do something accurate. So if somebody says it's wrong, just raise the hand and say your score is wrong. That's completely all right. And then I was like doing what's today's situation, because the techniques evolves, you know. So it was not taken into account like in the 2000s, but what about now? All right, more technique, but you'll see the ranking is still like pretty favorable to the chip. And then I want to also to highlight something is like what I call hidden threats. All right, because the bad guys have the tools. They have the tools, they have the money, and they do things, you know. And if we don't take into account invasive attack and reverse engineering based attacks, the point is like they continue to develop new tools, new techniques, and we are blind, basically. All right. So I'm just trying here to say, okay, here is the risk. Here is how it's evaluated. And here is what you don't even see. All right. Just like I want you to be aware. Okay. And then we can see together what we can do. So I expect lots of discussion after the talk. So let's start. So let's see how common criteria is taking into account those invasive attack things. And let's start back in the days. So first thing I have to say is like price of the equipment has always been an issue when it comes to evaluation. And in the 2000s, to start doing business inside this domain, you needed to buy tools. And some of them were more than 1 million euro already. So you see there's some kind of barrier of entry for doing this kind of work, which is pretty high. And, but I don't know. I would say that the price of a plane can be 300 million euro. And when you travel, you pay maybe 50 euros. And that's the same for this equipment. When the pirates are buying the equipment, it's not because they want to do one attack. It's because they know they will do several attacks. And you will see the return of interest is pretty good for them. So, but I will speak about that later. So what can we do back then? We could read ROMs, all right? So when we were starting, everybody who was starting to play with chips was extracting ROMs, and they were not even encrypted at the time. So it was like super easy. It was easy. So let's see one ROM, for example. So that's one ROM. And as soon as you could find the difference between zeros and one, the data are just there in front of you, you know. So if you have now a software which will extract the data, and basically you will get the ROM of the chip, and having access to the ROM, I don't have to tell you, it's something which is super interesting. All right. So different types of ROM, but the main thing is like you could see patterns like this when you were looking at ROMs. All right. Which to me is a clear indication that there is no encryption at all on the ROM, because you have like things that stays the same, you know, blank bits, blank patterns. And so, yeah, you could just extract the ROM, which gives something like this. It's pretty funny. Once again, you see all those patterns here. That clearly indicates that there is no encryption there. And the cool thing is like, you could extract this and you could try to convert this to, let's say the binary. But you had like several things to take into account. Like the order of the bits is unknown for you. So is it left to right to left, from the top to the bottom, or the opposite? What's a 0 and a 1? It's also not clear. You can say, oh yeah, there's a short circuit, so it's a 0. But maybe they invert the value in the buffers at the end. So it's pretty hard. But in fact, the thing was, it's so easy to just construct every possible version and then to look for strings. And guess what? The protection of ROMs was copyright vendor name. That's how they were protecting their ROM. Okay. Which is, I think, super nice. I think an attacker will see this and will say, oh, I have to stop there, you know. So it was pretty idiotic, but at the same time, looking for strings, was pretty nice because each time you could find the correct order for your bits. So that's pretty nice. What we also could do at the time was like reading Flash, all right? That was a bit harder, okay, because Flash bits are not visible under a microscope. You'll see it's partially wrong now. But at the time was like no way you could extract the bits by just looking at some pictures, So you had to do an attack on the target device. And to be honest, like this linear code extraction I was talking about is probably working on 95% of the chip, still today, I think, At least all the chips I tested are vulnerable. So, okay, let's do it. So basically you just take advantage of like your CPU is behaving like this, more or less, all right? And you have two types of instruction, and it's called linear code extraction. So it means you want to extract everything in the right order, okay? So basically you don't want to execute branches, okay? If I can execute only sequential instruction there, I win, okay? Because I will read address 0, 1, 2, 3, 4, and all the memory content will be extracted. So that's my goal here. All right, blah, blah. So I explained the same thing. Okay, so I want to execute sequential instruction for the address counter to be just incremented every time. On an example to make it maybe clearer, so that's a smart card from this time, it's pretty old. And that's the top view, and that's without the interconnection. So there is no interconnect on this chip anymore. And the fun part is like, you can see that this is the memory I want to extract. That's a flash, all right? That's my CPU. And in between here, I find 8 identical structure, 2 groups of 8 identical structure, which is cool. It's a memory. So I should have like read buffers and write buffers, So I think it's an 8-bit CPU. And that this is my buffers, basically. So you can trace the signals, and this is what you see. Yeah, they go between the memory and the CPU. So no doubt now, it's what I'm looking for. Okay, so now I need to find a way to be linear. So I don't want any branch to be executed. So it's old now. It's an 8-bit CPU. So basically, we can expect this to be an 8051 based chip. Most of the time it was like this. And 00 for 8051 is NOP, no instruction, and it's sequential. All right? So that's all I want, a sequential instruction, and I want to make it loop over it. All right? So basically, what you could do at the time is modify the chip with a FIB, just like short circuit all the lines that were going to the core. So now the core is seeing instruction 00 all the time. All right? And now I start my chip, but it starts to execute the first NOP and say, yeah, give me what's on the next address. So I'm probing just the data here, and I just dump the whole flash. All right? And this is something pretty cool. You could dump a lot of chip like this, I can tell you. At some point, we got some issues, because this was not working. This is like linear code extraction, stage 0, I would call it, Stage 1 was like taking into account like memory segmentation, because nothing tells you that the first thing to be executed is the address 0 of your memory. It might be somewhere else. And in that case, you could modify the setup by taking advantage of like reverse engineering, and that's a big word, the buffers. Okay, so this buffer is 42 transistor. The number is cool. And it's not a high count. So I can reverse engineer 42 transistor, I guess, and come to this schematic after. So this time I take the same chip, all right? And what I do is like I put probe points here. So when I'm probing a chip, people get confused sometimes. They think it's passive, I'm just reading data from the chip. No, that's wrong. I can inject also data. I can modify instruction on the fly. So if something doesn't behave like I want, or I don't want to execute it, I can just say, no, I change the code to something which is more likely to do what I want. Second thing is the buffers there. Looking inside it, there's 2 signals that controls the buffers, basically. So there's a read signal, and it's super nice, because I want to sample data here. So now I have a signal for synchronization, you know, read, that's cool, no? Every time it loads an instruction, it tells me you should sample the data because they are ready for you. I like it. Second signal, I think on this chip was enable, and enable was just so perfect, okay? Because enable was the signal to say that the input of the buffer coming from the memory will be copied to the output, okay? So if I don't copy it to the output, basically I skip an instruction, all right? But now if I do this, and the instruction which is here is sequential, it will keep executing this one. And now I'm linear again, all right? So with this setup, basically, you can control your linear code extraction and be linear when you want, skip instruction if you need to, and also modify some opcodes if you don't like them. So that's pretty powerful. But as you can see, I don't know if we should consider this reverse engineering, you know, it's not a lot of work there. And when we needed to do more, like on this example, for example, this is done with Photoshop, all right? So you have somebody who is now tracing signal on Photoshop. So before, you need to stitch the pictures, which is going to be your first nightmare, and then you will start to trace the signal, second nightmare, but that's not over, you know? You need to keep track of what you do. So basically now you need paper, okay? That's paper intensive to reverse engineer chips in the 2000s. And you will make mistakes, you know, because this paper is not the end. You want to convert this now to a VHDL model, for example. So you can be able to simulate what you just extracted from the chip, all right? But now do one error inside this mess here, and you go to the EDA tool, and you will see some errors. So some you can figure out, that's fine. But if you have remaining errors, you have to redo it all, okay? Because there's no way of tracking your error. So basically you are back to Photoshop, tracing signal with your paper to check if everything's correct and so on. And it takes months. It's super long. So the idea when it was coming to this was like really to filter out the amount of reverse engineering you had to do. So this is from the training I was giving there the last 2 days. And the idea here is like when you have a memory you want to extract, you need only to follow one of its outputs to do what we just said before. Only one. Because in fact, at some point, you will find some structures like multiplexers, for example, and by following their control signal, you will find the whole bus, okay? So no matter how many standard cells I have before, here I will find the whole data bus, alright? So the idea is to find the data bus after encryption. After the data are decrypted. So here is the clear data bus. And I have to say it, the key doesn't matter. All right? Key generation, the pirate will not care about this. So it's maybe unnecessary to have like super high-tech system to generate a key when the pirate will just like skip this part, you know. What he wants is going there. Okay? So let's see how this can be translated in the common criteria world. All right? So basically in common criteria, you have like two sections, like finding the weakness and just like exploit the weakness. And for all of them, you have like a few criteria, 5. And you have to rank them all, and it gives you a score. And basically, you want to be there. All right? So now let's try to put a mark on the attack we just did. And the mark will be this one, 44, residual threats. All right? So if somebody comes to you and say, oh yeah, on your chip there is this weakness, the guys will say, residual threats. That's how it's called. And most of it comes from, you will see, for example, this 9 here. Because it says that to do this attack, I need to know a part of the circuitry. But I don't know it before I start the attack. I recover this information. So I don't know why I take a penalty of 9 points, because I will recover the thing. It's like you are successful in the attack, so you have a penalty of 9 points, which is bad. I mean, I think it's not the way it should be. But anyway, so despite the fact that during the 2000s, I can say pirate cards on payTv, every 3 months a new one were issued. Okay, so that was a lot. That's French. Sorry, I didn't find the English translation, but I think it might be somewhere on the common criteria portal thing. But anyway, that's the important thing: residual threats. All right. How is it today? That's the next question now. So I would say that first of all, to get equipment is much easier now than it was before. All right. You can lease equipment. You can rent equipment. You can go in service lab that will do the work for you. Or you can rent time there. So you do the work in a lab that is not yours. So all the price that are linked to equipment is becoming super cheap. All right. You would be surprised. I mean, by the price of a certain task. I mean, yeah, there's an example here, like 200 euro for an hour of FIB time. Okay, that's what, let's say I'm working let's say I'm working a lot and it's 2,000 euro a day because I work 10 hours and I need the FIB for 10 days. That's 20K, you know, that's the price of the attack finally. All right. So 20K is still a lot of money, you know, but I mean, do you consider that something which is inside a secure application, whatever it is, eGov or, I don't know, control access or whatever, which will be in the field for 10 years, can afford this kind of things, you know? I mean, I can afford this as a pirate, all right? Okay. The big thing is like now the pirates are using automated tools, all right? And they have the tools since a long time now. So I don't know how the tools are, if they are good or not. I suppose they are, you know, because they are like dumping chips one after the other. And the idea is like, if I want to be able, with my company to evaluate this kind of security, I should have the tool also. So basically we were building one, which is called Chip Juice. It was called RS before, but RS is on Mac OS 6. It's a proof of concept, let's say. And with this software, basically you take picture of your chip and then you will extract the vias from the chip. You will extract the lines from the chip. You will extract the standard cells from the chip. And then you will build a catalog for the standard cell that can be reused for other chip of the same manufacturer. So that's also important to say. Chip designers are reusing things all the time. So I think like the reverse engineer can do the same, you know. And basically when you have this, you can detect all the instances of the standard cell on your chip and add the interconnect to get to netlist, all right? And that's your output now. You have the netlist of the complete circuit, which is kind of cool, I think. And because of this, I will take 9 points penalty for common criteria certification because I did it myself, you know? No, it's kind of weird. Of course, you have also the GDS2 file of the chip. So that's basically the mask layers. So you can load those inside an FIB, for example, and navigate from this, okay? Which is also giving you superpower, I suppose. All right, so how did it change my world? It changed because, for example, for ROMs, when they were starting to get really big, and when I say really big, it's maybe 5,000 pictures there, right? And I need to scan this with a SEM, which will distort the picture. Too bad, okay? I would need some more tools and things. So the way ROMs are extracted really changed. Nobody's trying to even like stitch the picture together before. You just extract the bits from every picture and create the raw binary like this. But it doesn't stop here. So now we have like, this is maybe a bit like complicated, but anyway, I'm not talking about this in full detail. But I want to emphasize and to say one thing. Now, you don't need a FIB to read most of the ROM, even if they are encrypted. The pictures alone are enough, right? Why is that? Is because if you take a ROM is basically bits. That's zone numbers 3 and 3. An address decoder, which is this part in the middle, and the output of the ROM, which are there, all right? So basically, if you can model the whole thing, so model the bits themselves. So you see here, the bits are just like a short between two vias or not. So it's easy to see, kind of. And then you can reverse engineer the whole address decoder circuitry, which is composed of stripe of things that address the bits more or less. You can get this. And at the end of the day, what you want is having a model of every of those different blocks. Okay? if I have a VHDL model of this, I will say, here is an address, and the addressing logic will find the bits for you. It will filter the bits, decrypt the bits, and give you the decoded value at the address you specified. So basically, we do this by using a VHDL model of the chip, because we extracted the VHDL model already, you know. And yeah, that's some kind of simulation where at the end you have finally the bits, you know, what's the information you wanted to have, and in clear, and in the right order. I mean, in any order you want, because basically you are now simulating the chip. So that's pretty new. Reading flash, same thing. So Sergei Skorobogatov, was coming here to present his work with passive voltage contrast. So passive voltage contrast is something you can do inside the SEM with a in-lens detector and by setting the parameters correctly. But at the end of the day, when you look at the flash, this is what you see. All right? So I see clearly the zeros and one now inside my flash. So to me, that's very bad. This thing now exists. It's really bad. So I cannot tell what is the lower tech you can use. You can read with this technique, but I can say that's far below this already. Yeah, so if you can read the bits like this, it may be still encrypted, but maybe you can get the netlist of the decryption circuitry, and bingo, you do an analytical method on this, and you extract the content of the flash. If you cannot do this for some reason, you can try to do a linear code extraction. So I took what I did in 2015, and now if I have to do it, once the pictures are taken, I just put this in the software, and then I press a button, which will say, you should look here. And that's the correct place to extract the data. So in like, I don't know, 5 seconds of time, it's a script now that says, this is what you should look at, all right? And those same scripts are also there to find all the decryption circuitry before. Okay? So again, I think it's like much frightening that what we had in the 2000s. But let's see how this reflects in the common criteria evaluation now. Before, 44 points. Now, 42. Residual threats, again. But I gained 2 points. I'm so proud, you know, and I just got more points because of the time, which is now smaller. Okay. But there's a thing, you need to prepare pictures. Okay. You think that delivering a chip is an easy task. It's not, you know. So just because you do this now, you have like maximum, you have a huge penalty on time. But okay, why not, you know? But again, some of the product will stay 10 years in the field. So if after 6 months, one of these methods I was showing to you is working, the chip is compromised, no? I don't know what you think, but somebody can just dump firmware from it, and then it's like, do what you want. Yes, sorry. I wanted to know what was the explanation for it. And the explanation is called invasive attack. I think it's the correct word. As soon as I say that I will perform an invasive attack, and even before I start working, this is my ranking. 33, all right? Because, yeah, they will say that because I will extract information, like the netlist of the chip, that's my initial penalty there. And of course, I'm an expert. And of course, the equipment I'm using is like, doesn't exist, you know. Maybe I stole this from some alien spaceship that was next to my home. The only thing which is good is I don't need really a lot of sample. So that's still okay. But you see, just because of these 3 factors, I scored 33, which put me already inside the residual threat thing. So I'm a residual threat, but I didn't even start to attack the chip. Okay? Which basically means that common criteria does not evaluate for me invasive attack at all. Okay? So when they say this to you, they are lying. Because, yeah, 33. By default, you know, that's before you even start. So I don't know what to say about this. To me, it's, I don't know, something's broken here. Anyway, it would be just correct if it was not the end of the thing. So all we discussed so far is, I would say, known. You know, it's not something like completely new, completely like the thing you never saw before. But we have also to think of like few things like equipments, for example. So that was a probing station back in the 2000, you know, with like tungsten needles that goes to the chip. Okay, so that's how we can get data out. Soon enough, they were more looking like this. So that's a custom setup with like, the needle is this long now, just like to have like a smaller capacitance due to the needle. The needles are, we were making the needles ourselves, you know, buying tungsten wire to be able to sharpen the tip as thin as we wanted to have. You have the buffers, which are very close to the needle with like transistor for disconnecting them if it's necessary and so on. Because yeah, you want to get data even if the chip is running fast. Okay. Of course, if you do invasive attack, you can also take control over the clock. Like this, you dictate the speed of the chip, which is also something that can be useful. Yeah, sorry. The main disadvantage of those things is like, I can't place myself more than 5 needles on a chip. Okay? I tried, it's hard, and when I put a 6th needle, I saw one over which is just flying away. So that's not super convenient, you know. It would be cool to be able to put like, I don't know, let's say a 16 needle on a 16-bit bus, okay, or 32 needles at once on the bus to be the code yourself, okay? I'm giving the code because now I'm the bus, alright? And the truth is, like, some of the guys out there can already do this, okay? What you do is you basically add one extra metal layer on top of your chip, alright? So here you have like, the data bus is just underneath this line, basically. And all of this is lines that have been like added to the chip, so we can directly control the bus, alright? Did you hear about that? It's in the fields, it's at least 10 years. So, and I think it's pretty bad because it gives some kind of like superpower, again, to the attackers, because if you can sit on the bus, basically you control the instruction flow. You are the code now. So I can just say, give me what's inside the flash, can you just give me the keys or whatever, you know, it's pretty powerful. The chip, you mean? It doesn't really matter. This is 90 nanometer chip. And the lines here are just like, it's a photolithography that was done on this with a UV laser. And the minimum size of line that we could reach was 4 micrometer, which means that basically if you have to put like 200 connection there, that's feasible. And those lines here are gold lines, but turns out that with silver you get better results. But now you have the PCB here, so I don't need needles anymore, okay? And my buffer can be sitting on the same PCB, alright? So it's like I could take the plane and I can still, you know, microprobe my chip inside, okay? So it's pretty efficient. Semi-invasive attacks. I need to speak about semi-invasive attacks because they are evaluated, I think, for common criteria. And to me, the risk is not the guy who can buy some Hamamatsu equipment for $1 million, you know. It's the guy who can build this. All right. So you can build this yourself. It's a do-it-yourself laser station, which had this is a microscope. You know, the camera is on top. This is an objective, XY stages. A laser with an acousto-optic to filter out the pulse you want to keep, you know, because you want to control your attack at some point. And this picture here has been made with this setup, basically. So it's using a technique which is like from failure analysis, OBIC, optical beam induced current, because when you shoot with an infrared laser to a chip, basically you will create electron hole pairs that can move if there's an electric field, so that's called current, basically. So with the laser, you're switching transistor, and the charge will escape. So if you take the voltage across the chip, it's passive, you don't need to power it. You convert, you have the position and the value, so the voltage, you convert this to grayscale, and bingo, you can make a picture of the chip. The good thing with this is like, it's always hard to position the laser when you do this kind of attack. You need some kind of like making sure that if I say shoot here, it will go at the correct position. All right. But if you do oblique for making the picture and you say to the same laser go there, your positioning is pretty good. It's not perfect, but it's super nice. So, okay. It's not so bad when you look at it. It just means that you can build your own laser station. But now let's think about like the guys who can use reverse engineering. All right. So basically here what we see is like all the standard cell on one chip. Okay. So there is like, I don't know, on this one, I think it's like close to 50,000 cells. All right. And it's a secure element and blah, 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 blah. It's super nice. If I shoot with my laser on some of the cells, which are known to be combinatorial cells, so all the AND, NAND, XOR, you name them, as soon as the laser pulse will end, the effect will also be stopped. All right. So basically, what will happen is like maybe I inject a fault somewhere on the chip, but before it reaches the next register, when it will be stored, the effect disappeared. Okay. It's pretty sad, no? So how do you evaluate this? How do you know if this chip is like susceptible to this kind of attack? It's pretty hard. So let's be dumb, okay? So what I want to do now is I want to test every point, you know? I want to scan basically. Tuk, 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 tuk. So I will need to choose like a step for scanning, and my step will be small, of course. So you will end up like with maybe 2 million trial to 2 million points to test, you know, which is maybe a lot, you know. And this thing, it's 2 million points to test per clock cycle where you want to test. So you want to test on a specific instruction, maybe. So you need for each time to reach this specific instruction, make the test, then move the stage, relaunch the system, wait for the specific instruction, fire the laser, and see if it's passing or failing the test. All right? That could be super long, if you ask me. At the same time, if you shoot the same laser on a register or on a latch, you know, these things that contains the memory elements, if you inject a fault, it's registered. That's the point, okay? So if you ask me, if you want to evaluate the resiliency of this chip against laser attack, only shoot at register, okay? So now, if you have like made the proper reverse engineering, you can filter this GDS2 to keep only the position of the features of interest. Okay, I said register, but maybe it's something else for you. For me, at least, it's registered. But now I have this do-it-yourself station. If I can overlay this on top, you know, wow, maximum power, you know, because I can shoot at registers. So instead of having to try 2 million points, you know, like randomly, I never know. You know, it's always hard to say to my customer, oh, you want me to test this? Okay, you want to give me money basically for me to go fishing? You know, it's bizarre. So at the end of the day, if you can filter this and overlay this picture on top of the oblique picture, you have like the perfect situation where your laser will only test those 2000, I think was 2000 points. Okay, but they are clearly known. Okay. So we call this smart gun, you know, because it's, I think there is a gun that is called like this, you know, which is super, super fancy and all things. Yeah. And we want to emphasize this because we really think that it can save like 90% of time for an evaluation and get the same results, if not better, I think. All right. Non-invasive attack. It was so good, you know, when you could use the clock, you know, to inject a fault inside the chip. All right. But problem solved. Everybody's using internal oscillator. Okay. So you don't have access to the internal clock. So, okay, you can take your FIB and just take control over it. That's not easy, I would say. But what you can also do is like, if you can make a reverse engineering of the chip, you can study the clock tree of the chip. All right, because the clock has to arrive everywhere at the same time, basically. So they distribute it in a specific way on a clock tree. But if you can study this, and I want to inject a fault only here now, and I have a FIB, I can modify the clock on this branch only, okay? So the effect is no more global, okay? But it still has a clock glitch. So the clock glitch is just made for preventing something to happen or taking a wrong result inside a register. So that's another thing you can think of. And it's true to some extent for VCC glitching also. If you have a big SoC, I'm pretty sure the power distribution will be also tree-based. All right. So select your branch where you have like, I don't know. I always have this example. Once we had a chip with like 3 different rings, it was an SoC. And to get access to JTAG, if you could disconnect the power for only the processor during the JTAG authentication, bingo, you are in. So that's pretty powerful attacks. And now, instead of doing this from outside, you can do it from the inside and target specific structures. What would be a talk about IC security without a shield? Shield is one of the only countermeasure against microprobing. If I cut this line, the chip will destroy itself. Okay? Too bad. But now, if I have the netlist of the chip, I will find a register, which is basically a flag that says the shield is okay, or there is a violation. So I can now take my FIB and corrupt this register, and say, everything's okay all the time. And now I can just like completely remove this. Okay. So that's the kind of countermeasure that doesn't work. Yeah, there would be so much more to say about shield, but, not now. We spoke about passive voltage contrast. All right. You can do really, really cool things with passive voltage contrast. That's a ROM here when they were using dummy vias to encode zeros and one. Okay, so you see vias that are completely white and some others that are gray. Those ones are just half of a via. Okay, they don't reach the layer below. So that's how they create zeros and ones. So basically, the white will be ones and the gray will be 0. Okay, so there's an extra cost to do something like this for sure. But for the attacker, can you see zeros and 1? Yes. So it changed nothing. So for all the countermeasure camouflage techniques that are based on using dummy vias, it doesn't work. Passive voltage contrast is there. Reading flash, passive voltage contrast. We saw this before, thanks to Sergey. It's pretty cool. But here, that's also passive voltage contrast, but that's applied to a chip that is running. All right? So let's imagine that now this is a picture of the chip where I have 2 colors only. Black is everything that is logical 0, and 1 is, and white will be logical 1. And let's now imagine that you can see what's going on, like almost live on your chip. All right? You see a counter over there, by the way. Let's see now that I have like the GDS2 of the chip, because I could extract the file. I can annotate the file, put this on top, and now I'm probing all of those lines at once. All of them. Okay? Do you think this is scary? I think it is, but I think it's nowhere near coming to common criteria evaluation. Too bad. Wanted to show you what's an extracted netlist. That's an extracted netlist from a chip. Okay? So, but basically it looks like this. There is, I don't remember on this one, but we did reverse like, the core. So the core is somewhere, but there's also like the memories, charge pumps, and a few analog structures there. Because this chip could do a RFID, so we also reverse that part. But, when you look at the netlist for the core, for example, it's just a big mess. Okay? And what you want is just like hierarchize the information. And that's a tricky problem. It's a tricky problem, but when you can do it, every time you have like a new block, like this block is a combination of like a lot of standard cell. If I have another chip, I can search for it. All right? So I save time. I build also my library like the chip vendor is doing probably. It doesn't stop here, because then you can do data mining. Okay? So that graph is basically 600,000 chips. All right? And we can classify them, according to the rules we want. But the idea is like, for example, What if I can find a chip which contains a crypto processor and the same chip without? All right. It would be interesting to get like the two netlists and to make like some kind of hard diff, you know. You all know bin diff, I'm sure. So hard diff would be the same, you know. Tell me the difference between those two netlists, and the difference will be the crypto processor. So now I know where it is. I don't know how it works so far, but I know where it is. So I can start to play again silly games, you know, trying to reverse engineer, to know where to put my EM probes, or to FIB edit to change something inside. You name it, okay? But you can build libraries like this. And this is like also not so known. All right, that's another example, so I'm not sure I have time for this, but JTAG on SoC, you know, because I'm talking a lot about like secure elements, smart cards, and these chips. Because for me, that's the one, they are called secure, you know, so that's my target, you know, that's my initial target. But SoC sometimes, it's also good to look at, you know, and people want access to JTAG most of the time, all right? So when it's locked, and if you can do reverse engineering, here is like two methods to basically find the control circuitry for JTAG. And if you can find it, you can try to understand the locking mechanism and what to do to just like enable JTAG, you know, like permanently for you, get some more access to the chip. But that's just an example. I mean, these all techniques would apply to FPGAs, and extracting bitstream would apply to any electronic device, kind of. Yes. And yeah. So this is how bad this, the thing are getting to me. And the thing is like, all right, so what's the point? Okay. So the point for me was like, I wanted to change common criteria back in 2013, you know, but in real life, lots of things are happening, okay? And I think like the pirates before were doing payTv, you know, it was such a cool business, you know, it was really entertaining. But now people want to do this, you know, making copies, you know. If I can copy a printer cartridge, basically I'm rich, you know. You would be impressed. The market, the pirate market, it's not pirate. The off-branded market for printer cartridges is estimated to be $7 billion in 2016. That's how much money there is now. And it's like, how do you produce those cartridge? No secret. You take the official one, invasive attack, dump the code, and emulate it on another device. Bing, you are there. So it's a residual threat anyway. Just keep this in mind. But you could do also like illegal copies. I mean, like for everybody who wants to build a fucking nice IoT product and put this in the field, if it's a good product, I expect the product to be counterfeited pretty fast. Okay. And we can add this to the criteria to know if a chip is secure, because it can be a measure of the security of the chip. Okay, there's a counterfeit, but at the same time, it's a measure of the success of your product. Okay, oh yeah, it's counterfeited, it's a good product, you know. But it doesn't stop here. Of course, you have all the problems with like the eGov application or the conditional access things. You know, some people wants to send a satellite in space with off-the-shelf device, you know, so they need to be sure that nobody is trying to connect to a satellite, for example, or just maybe your YubiKey, or I don't know, your Ledger wallet. I think Ledger is sponsor, so just like a private joke. But it can get to the point where an invasive attack can also be used to get information about the device. All right, it's the goal is maybe not like to hack the device. It's like a first step towards something which would be bigger, okay? So getting, for example, the firmware of a few critical systems, I would say, can be used for going to the point where you can make remote exploits, for example. So basically, to make it short, you know, what I want to say is like, IC is not a secure world. And if you want to have secure firmware, you need to make sure that your hardware is secure, because on top of this, you cannot patch the hardware. Okay, so if I find something that will lead me to the firmware, for example, I don't see what you can change in your in your device to prevent this to happen. That's too late. All right. So to me, it should be considered a bit more. Oh, it's white. I didn't know I had animation here. So basically, just like if we take like attack efficiency and cost of the attack. So non-invasive attack to me are just like there. You know, it's you don't need to invest a lot of money to start. You know, but the efficiency of it is discussable. You know, it's arguable at least. But it's something that is considered like secure and certified, you know, most of the time. So that's good. If we look semi-invasive attack, same thing, you know, you can make evaluation that will say that it's good and you will get like a nice certification. For invasive attack on the other side, okay, that's expensive. Okay, that's much more expensive than the rest, I would say. But the price was going down from the 90s to today. It's still expensive, all right. But the power you have is like, I think that's the most efficient attack, okay? I don't know, like pirates in the field that would start with like glitching when they know that, oh yeah, I should be able to extract the firmware with an invasive attack. It's almost a 100% guarantee, you know? So that's where to go, I think, for them. Anyway, no efficient protection against invasive attack. Yeah, this is sad. There's not so much on the chip, not so much countermeasures and things like this. And there's also no solution to properly evaluate the thing, I think. A lack of method, maybe. But at the same time, just to conclude, this is what should be taken into account. So the exposure. When you have a chip which is used in different markets, one of the market could be like super exposed, you know, and now it comes to risk management. I did a chip, you know, it's a super nice chip, but maybe I don't want to put it in this market. Like this, I can say it's secure because on the other market, I'm safe, you know, and things like this. But this is risk management. You really need to make some choice there. What's not taking into account is the learning curve for the attacker. An attacker from now is like a bit different than 20 years ago, okay? We are not using Photoshop anymore to analyze chips, okay? That's gone. And Photoshop is not running well on top of this. Return of interest. I said, let's imagine a hacker, okay? And he wants to start the business, you know? Maybe he will spend like, I don't know, 5 million euro to build a lab with only new equipment, state of the art, super nice. If he goes to the printer cartridge market, first attack, he will have the 5 million back. That's how it is. So price of the attack, okay? To some extent. So, yeah. I mean, so then there's a few other things, but effect on other attacks, maybe backdoors, you know, it's a big topic right now. And to be honest, so this is what should happen, and it doesn't. So on our side, I'm here today for trying to raise awareness. You know, I'm giving training and stuff like this. We are doing security assessment, benchmark, and stuff like this for chip vendors and for integrators. And we have like a good response from the integrators themselves, you know, and they're the ones that push now on the vendors to say, oh yeah, you should build better products, you know, because this risk exists and it's maybe why I'm pirated over there. And yeah, I don't know. I think the certification schemes should extend the analysis surface to invasive attack and reverse engineering based attack. And if you can help me on that, I'm really happy. If you can give me ideas, because I have no idea. And I will end up my talk like this. And thank you. And if you have any question, I will be super happy to answer.
Well, thank you very much. Who wants to start with the first question? There's always someone.
Hi, thanks for the talk, Thomas. I have a question regarding the maximum netlist size that you have automatically successfully extracted with chip juice. And maybe you can comment also on which process size. Was it 90 nanometers or was it even below?
No, we did, we did 40 nanometer. We didn't have a request for something which would be a smaller node. To be honest, I don't clearly see where would be the limit for us right now. the tool doesn't care, because you get pictures. So if you can make like deprocessing and pictures, that's all fine. All right. So it all comes to the point of like, are you able to generate the right pictures? And we've been adding to the tool everything to handle bad pictures. So if you need like I don't know, like several samples to image one layer, that's fine. You just put the pictures and they will be put together and everything. So I don't see a limit there. And then for the size of the netlist we can extract, I don't know the upper limits, to be honest. So I don't know. We have like, we started with a chip that was like maybe 4,000 standard cell, which is like super small. And that was like, was not so long ago, but now we are more on the size of 500,000 cells. Which is already a decent chip. And I'm not counting memories or anything. I'm just speaking about the core.
And how long does it take for 500,000?
It's almost the same time. So basically, I'm not speaking about the lab thing, but to go from pictures to netlist is under a month. In almost every case. What takes time is to rebuild the standard cell library. But it's a one-time job, okay? Once you have it, you have it. So, still fast.
You want to go first?
Well, great job, thank you. I noticed that most of the talk focused on architecture with CPUs and ROM and data to be extracted.
Yes.
There are situations where basically for example, maybe a crypto engine, there is a finite state machine and the sequential logic that implements the engine, for example, and the key might be either embedded into the netlist basically or into OTP cells. For OTP cells, I think it should be quite easy to recognize what things are, but do you apply the same approach for netlist also for getting the key out in that case? How would you process that specific case where the key is embedded in the netlist basically?
We would proceed the same, and we will see that. So I don't know, hard-coded keys. There are a few ways to build embedded keys, but you would see that you would find them basically inside the netlist.
So the process is basically the same that you are applying. Okay, thank you.
Okay, one more.
So one of the latest developments in flash technology is 3D NAND, where layers of flash NAND are stacked onto each other. I was wondering, does that complicate dumping the content, especially if you consider some implementations where layers of heat-conducting material are implemented in between the layers?
So to answer directly, yes, it makes the thing different. So you will not use passive voltage contrast for this flash because you will fail because you need to reach the thing, So it can be really complicated to separate the different layers and do this. So I would say you wouldn't use this technique, but you can still try to hack it from the side, So get to the bus, and ask for the data and get the data back. So that's what would happen. And I would just balance this a bit because it's far from being inside secure device, what you're describing. I would like to see a 3D flash inside a smart card, for example, or inside a secure element. Never saw that, So it will come for sure. And it will make my life not so much difficult, because, okay, I cannot use passive voltage contrast, but I can still do invasive attacks, So.
What about dynamic stacked RAM like HBM, where you cannot ask the bus for the data because the system has been turned off, but you still want to do a cold boot attack? How would you approach that?
I don't know. I have to think. That's really specific, and once again, that's not something that is in the field. So I can only speak about what I saw. That's my point. I'm doing reverse engineering, and I can't read, so I know nothing except what I see on chips.
Okay, thank you.
Well, thank you very much. We're going to move on to the next talk.
Thank you.